Geometry students, we have 5.3 using angle bisectors of a triangle. And once again this week, I'm hoping that you watch the short video first of me folding the triangle up to find angle bisectors and drawing those angle bisectors and looking to see that they all would meet, okay? So again, this is what's kind of funny in these notes is it never defines angle bisector. Okay, so this angle bisector, we probably should say, is some type of a line or line segment or array or something like that. I'm just going to shortcut and say line that cuts an angle in half, right? And when we say in half, in equal halves, right? So, okay, I'm going to tell you right now, the chance that I can draw these accurately are slim to none. It was hard enough folding them, right? But so you come through this angle and you cut that angle in half, right? Come to this angle and you cut that angle in half. And take this angle and we cut this, notice how far off that one is, right? It's not even there, but I cut it in half. So my picture looks something like that with my angle bisectors, right? Cuts all those angles in half. So our one vocab word that they did give us today was incenter, and it's the point of concurrency where my three angle bisectors meet, okay? And we know from the example I did in the other video that it didn't matter if it was an obtuse triangle, a right triangle, or a acute triangle, always those angle bisectors met inside the triangle. Okay, so a few notes here. Before we do the full triangle, we're going to work on just a simple angle with one angle bisector because there's properties just inside that one angle. So if a point is on the bisector of an angle, so here's my angle bisector, this line right here, okay? Let me highlight it maybe instead. So there's my angle bisector. If there's a point on that bisector, anywhere on that, it will be equal distance to the two sides of the angle. Okay, so we're looking for the word sides right there. Now, remember, if you're equal distance to something, you take the shortest distance to it. So you'll notice that I have this right angle there, and then this is equal to this. But it has to be the right angle to say I'm doing the shortest distance from that point to the line across. So DB is going to be the same length as DC. Okay, so it's the shortest distance between those two. All right, then we followed right away with the converse that says if there's a point on a line that is equal distance to the sides of the angles, then it has to lie on the bisector of the angle. Okay, so if D here is equal distance and perpendicular, because that's the shortest distance, then we know it has to be on the angle bisector, so it's cutting that angle in half too. So key things, there are two. You have to be perpendicular to the sides, not anywhere else, but to the sides, and equal distance from the sides, then you can be on the angle bisector. Okay, and I should give you a heads up, I can't get my stylus to work right now, so I'm doing notes with my finger, so I'm sorry if it is a little bit sloppier than normal, as if it wasn't already sloppy. All right, we're looking for the measure of angle CBE, that's this angle right there, okay? So we're looking for a few things here. It says EC is perpendicular, it looks like, to BC. I see a right angle right there. I have ED is perpendicular to BD because I see a right angle right there. So right angle here, right angle there. That means those lines are perpendicular. I also see that EC and ED are both 21, so those are equal distant. Okay, so they're perpendicular and equal distant. So that means that BE is going to bisect that angle because it is an angle bisector. Anything that is the same distance away and perpendicular is an angle bisector. So then we can look at our picture and say, well, if this side's 31, this side should also be 31, right? So both of those sides are exactly equal. CBE is going to equal DBE. And we get both angles are 31 degrees. All right, let's peek at our next page. All right, we've got to have a real world problem, right? So, you know, the next time that you are a spider or a fly, think of this problem. So a spider's position on a web relative to the approaching fly in the opposite side of the web forms congruent angles as shown. So you'll notice down here, I see some congruent angles, okay? Will the spider need to move farther to reach the fly to the right edge or the left edge? So right now, the spider is on this line we call the angle bisector. So which side is closer, the left or the right? And so it says the congruent angles tell you the spider is on the bisector. And if we know that by the angle bisector theorem, the spider's equal distance from both sides. So it really doesn't matter. He can go the same distance, right, on either side. So he doesn't really matter. So the next time you're a fly or a spider, remember that. Stay on the angle bisector. Then you can go to either side. All right. For what value of x does P lie on the bisector of J? So the rule is if P is going to be on this bisector, then these two have to be equal distances and perpendicular. But equal distance is what we're looking for right now. So we want x plus 1 to equal 2x minus 5. Solving for x, I'm going to subtract my x. I get 1 equals x minus 5. Add my 5, and x equals 6. So when x equals 6, we're on the angle bisector. Any other value, we're not on the angle bisector. Okay, one little theorem down here, and I've got so much I want you to write and kind of comprehend what's going on here. So we had a similar box in 5.2 notes, okay? So think about this one. This says the angle bisectors of a triangle intersect at a point. This point, by our definition, we call that the incenter this time. And once again, I didn't stress this earlier in the notes, but when I told you yesterday on the perpendicular bisector goes with the circumcenter, and you want those two words to go together in your mind, circumcenter, perpendicular bisector, today I need you to keep in mind that the angle bisector goes with the incenter. Those two words need to closely relate in your mind, angle bisector and incenter, okay? So these angle bisectors all meet at an incenter. That's this point P right there. And the key here is this one is going to be equal distance from the sides of the triangle, okay? So we had to draw new lines down to the side, over to the side there. And notice all of them are perpendicular because the shortest distance from a point to a side has to be perpendicular. So that incenter now, the rule is equal distance to each of the sides, okay? So PD is equal to PE, and it's also equal to PF. Okay, so what we have here is it's the incenter. Okay, I'm going to try my best to draw. Can't promise what this is going to turn out to be. But do you remember yesterday, in fact, I'll come over here to the margin. The perpendicular bisectors intersected at a point equal distance from the vertices, okay? So yesterday, if I can kind of draw this, and it's not going to be great, but all my perpendicular bisectors, right, met at this point. All right, you think it's hard to draw to start with. Draw with your finger. It's rather ridiculous, but you know what? We'll take what we can get. Okay, so you remember from yesterday, all those perpendicular bisectors, they met at a point called the circumcenter, and it was equal distance to the center, to the vertices, which means this circumcenter was the center of a circle drawn around the triangle, okay? Not great, but it kind of gives you that idea. Today, okay, I'm just going to try this the same way. All right, today with my triangle, I'm going for the angle bisectors, right? So this is where my angles are cut in half. And this is going to be really great because that one definitely was not where it should be, but it's going to work. Okay, today we have the angle bisectors, and they meet at the incenter, okay? And this incenter is equal distant to the sides, which is the center of the circle drawn inside of a triangle, okay? So the sides make the inside triangle, and they belong to the incenter and the angle bisector. The vertices make the outside triangle from the circumcenter, okay? So make sure you get these margin notes. Make sure you get these two notes over here. The incenter is always inside the triangle. Remember in yesterday's notes with the perpendicular bisectors, I drew 3 different triangles, and I drew the perpendicular bisectors every time to show that it met inside the triangle, on the triangle, and outside the triangle. I don't need to draw all 3 right now for the angle bisectors because they always meet inside the triangle, no matter what shape. No matter what shape. They're all triangles, no matter what type of triangle, whether it's acute, right, or obtuse. All right, last page, and it's legitimately the last page today. This is a quicker one. Okay. It tells us in this triangle, L is the incenter of the triangle HJ. Okay, notice it's way down here. So if I was going to draw the triangle, the circle, it'd be just on that end down there, okay? We're trying to find LK, which is right here. There's nothing around LK. But I'm going to kind of highlight and make bigger this triangle right here, which has I, has H, and it has L there in the middle. And they labeled 12 and they labeled 15, okay? So I'm in this triangle right there. Well, the thing with this LK that I'm supposed to be finding, it should be the same length as LI, it should be the same length as LG. All those should be the same length. So if I can find this LI right here, it's the same thing as LK, okay? Because it is equidistant to the sides. That's what I'm putting right there. Okay, so our job is, let's find LK, or LI, and then we can replace it with LK. Okay, so we're going to find LI. This one right here. Okay, maybe it's been a while, but do you remember how I find the missing side of a right triangle? My notes didn't show up as I wanted them to over here in the margin, so you can't even see what I wanted here. If you don't know it, Mr. Pythagoras gave us this formula, a squared plus b squared equals c squared. So that's what we're going to use to find the missing side. When you're using this formula, the key is, on a right triangle, C has to be the hypotenuse, the side that doesn't touch the right angle. The A and the B can interchange. They can be either one of the other sides, but the C must be the hypotenuse. So in this case, and by the way, they wrote this formula backwards, C squared equals A squared plus B squared. That's what they want here. Okay. My C has to be across, so this is my C right here. I put 15 here. My A and my B, it doesn't matter. I'll call one X and I'll call the other 12. And I'm solving for X. So 15 squared is 225. I get my X squared. 12 squared is 144. Subtract my 144 and I get 81. And I want X, so I still need to take the square root, and it looks like my value will be 9. So if LI is 9 over here, then it's going to be the same thing for LK, so LK is also going to be 9, okay? So using Pythagorean theorem there. Maybe a little bit of a blast from the past. Been a while since we saw that. All right, couple more examples here. It says in exercise 1 and 2, find the value of X. So I see that my equal distance here to the sides, it's perpendicular. That must mean that this is my angle bisector. It's bisecting, okay? And if it bisects, that means those sides are equal, those angles. So 3x minus 5 is going to equal 2x plus 5. Subtract the 2x, add the 5, and I get x equals 10. All right, on the other side, on number 2, what I need to look for there is I notice that my angle is bisected, so I already see my angle bisected, and I have two lines that are both perpendicular, which means they're going to be equal distance to the sides. So if they're equal distance to the sides, I know 7x plus 3 is going to equal 8x. Subtract 7x, and I get x equals 3. Number 3 says, do you have enough information to conclude that AC bisects angle DAB? Now, this is what's super important. I see equal sides, equal distances, it looks like. But the problem is, my angles are not perpendicular. So I do not know if that is the shortest distance. So because of that, I'm going to have to say, I don't know what I was started right there. I'm going to have to say no, it's not perpendicular at the sides. It is so important that they are perpendicular at the sides and equal distance to the sides. If it's not perpendicular at the sides, you cannot have an angle bisector. All right, last one, it's going off that top picture from before, and it says back up on that top picture, suppose you're not given HL or HI, but you're given JL and JI, okay? So if you look up at that top picture, at your JL and JI, that's coming from this corner over here, basically. It looks like this. So J over here, I's here, and L is here. It says JL is 25, JI is 20. We want to find LK. Well, quick reminder, this LI, it's still LI, is still the same as LK. Okay, so that hasn't changed from that earlier example. But we have different numbers, so we're going to try to find out what this Li is, okay? Once again, I'm using a little Pythagorean theorem. A squared plus b squared equals c squared. Which one is my c this time? Across from the right angle always has to be my c, so that's 25. I don't care what the other two are. They just need to go into the other two spots, a and b. You can always interchange them and you'll be fine. X squared is x squared. 20 squared is 400. 25 squared is 625. Subtract 400. And I want just x, so I take the square root. X equals 15. So if Li equals 15, then Lk equals 15 as well, because they are equal. Okay? And that's angle bisectors. Okay? No systems of equations today, just straight up nice linear equations, right? So practice this time. I don't have a worksheet today. You're practicing from the book, page 313 to 314, 3 through 25 all. Let me know if you have any questions.